Well, welcome back. This segment is about measurement. And by measurement, we mean the ability of extending our senses way past what you and I can just see of that which is right before us. Now, before I get into this segment, I'd just like you to know that this is going to run a little long, so if you want to break your viewing up into two segments, that's probably a good idea. All right? Now, there's 5 topics that I want to address with you in this segment. And as you can see, it would be ethics, what measurement looks like, the concept of significant digits, scientific notation, and calculations. So let's dive right in. Now, first, what do we mean by a measurement? And as you can see, I have right here that we're combining numbers and units to describe some quantity. And keep in mind that a measurement is always going to reflect and only going to reflect the accuracy of the measurement device that you're using for that particular item. And as a result, there always is going to be some uncertainty in measurement. Now, with that limitation, we also have the wonderful opportunity of performing calculations on measurement. So we're able to extend what we understand about the physical world way beyond what is right before us. So with those introductory remarks, let me go ahead and get started in on ethics. All right, now by ethics, I mean what is right and what is wrong. 2 big concerns here. First, we never want to use measurement to steal from other people, and so by cheating on a measurement so that we can extort more money from them. That's wrong. And you can see it here. Proverbs 11:1 says that a false balance, in other words, intentionally false, is something that God hates. It's an abomination. And a just weight is His delight. And that's something that He brings a smile to God's face, according to this verse. The second idea is honesty or truth-telling. We don't want to say that this measurement we've made is more precise or more accurate than it actually is. So the idea of not stealing, of respecting private property, and also telling truth in our measurement. And in order to maintain these things, scientists have developed rules by which we consistently interpret measurements, and government also has a way of regulating and maintaining the accuracy of balances and other equipment that are used for measurement in the marketplace. So ethics is an important idea. Now we need to move on. What does measurement look like? Well, I want to focus on something that's commonly seen in the marketplace, and that's an electronic balance. When we take a look at this piece of chain here that's being weighed on the balance, we have certain digits, those which are actually known and are certain of what they are, and typically we're going to see an estimated digit, which is the 7 that you see right here. So there are certain digits, and then there are those that are estimated. All right, so keep that in mind. All right? So there are certain digits, and there's one estimated digit in every measurement that we make. Now let's move on and see what that would look like in another place. Here we have a nice, ripe, small cherry tomato, and you can see it's been lined up with the 0 centimeter mark on this ruler. So length is going to be one unit of measure, one type of measurement that we make, and the base unit for that is the meter. Here we're looking at hundredths of centimeters, this distance that you see at the bottom of the screen. And there are smaller marks that are here that divide centimeters up into 10 equal portions, otherwise known as millimeters. So if we wanted to report this measurement in centimeters, you can see it's less than 1, so it would be 0. You can see there's a 5 mark, 6, 7. It's going to be 0.7 something centimeters. And remember I said that there is one estimated decimal place, and so we're going to zoom in here and we're going to take a look at this distance right here, because as you can see, the 0.7 mark is actually not extending to the edge of the tomato, so we're probably going to be somewhere about 0.72, 0.73. again, we're estimating. Not everybody is going to make the exact estimate of that digit. I typically use a 2 and a 3 if it's closer to the smaller mark. If it's closer to the larger mark, I typically use 7s and 8s as the estimated digit. If I can't tell which one it's closer to, I'm going to use a 5. And so I'm going to call this then 0.72 or 3 centimeters for the diameter of this tomato. And again, once I know the diameter of that tomato, I can figure out its volume too, using math. Now let's go back to this idea of mass. Now, as you can see, we have a beam balance that's before us. And before we get started in measuring out what the cell phone actually is, I want to draw your attention to this little knob that's right up here in the corner of the screen. This knob is there so that when nothing is on the scale over here, that this end of the beam is going to match up with the 0 mark there. We need to keep in mind that if nothing's on the scale, then it ought to read nothing when all the weights have been placed there. Okay, so let's get down and take a look at what this measurement actually looks like. Get myself out of the way here. You'll notice that we have a weight for every place value, every power of 10. So this is going to be 100. And then in the tens place, we have 30. And in the units place, we have the 0. So we add those together, that's 130. And then we can go past the decimal point to less than a gram, and you'll notice that we're beyond 0.5 a little bit. So we have 130.5, and in the hundreds place, we're at the first tick mark. We'll move in here a little bit further. We're a little bit past that first tick mark, so we have 130.51, but you'll notice that the shadow on this photograph isn't the best, but the shadow of that pointer is just to the right of the tick mark. That's the 0.51. So I'm going to estimate that again as a 2 or a 3. So we're looking at 130.512 or 130.513 grams for the cell phone. All right, and you might want to take a moment, write that down, as we'll come back to that in a little bit. And so that's how a balance is used to, again, we have certain digits and then we have those that we're going to estimate. Now, there's an important exception that I want to make as we go ahead and look at measures of volume. Cubic centimeters and milliliters are that which we use for measuring volume of liquids. But take a look here. This is a 10 milliliter graduated cylinder, but the marks that you see here are not in powers of 10, but they're at 0.2 of a milliliter each. And so our estimating that 100th digit, it's just not going to work in this case. We're going to need a more precise graduated cylinder to do that. Well, let's go ahead and look at the measurement that we find here. It's a copper sulfate solution, and you can see that we're above this middle tick mark, the larger one that's evenly placed between the 2 and the 3. Do you see that? So what unit is going to be between rather a 2 and a 4? You guessed it, it's a 3. So we're going up then by 0.2 of a milliliter from the 3 mark. So 3.2, 3.4, we're right about 3.6, maybe a little bit past that. But we're going to have to be content with 3.6 milliliters due to the markings that are on this graduated cylinder. And I want you to notice something further, because the surface of this aqueous solution, which is a water solution, is curved. We're going to rely upon the bottom of that curved surface for our measurement. Water has the wonderful properties of cohesion and adhesion, which we'll look at in a later program, and it allows water to be drawn up by itself into the roots of plants. But it's also going to happen at a graduated cylinder. This has been calibrated, so we're using the bottom of that curved surface or meniscus. So again, this is going to be the one exception that we looked at the beginning of this segment. is that we have certain digits and we have one estimated digit. Again, this is going to be an exception to how we've done that. Now we're going to move on to another topic, which is the fact that not all digits are considered significant. Kind of a scary idea. What do we mean by significance? In other words, one that we're going to include in the measurement. And there's 5 rules that scientists have come up. I'll get myself out of the way here. There's 5 rules that scientists have adopted that are going to keep us legitimate in reference to measurement. And the first that you see is here is that all non-zero numbers are considered significant. Now, what do I mean by a non-zero number? Well, all these, there's no zeros in here, so we're going to consider this whole measurement to be significant. The 22.741892 is all significant. There's no zeros there. Now, zeros form a significant problem because sometimes, as you know, zeros are placeholders. Keep that in mind. Zeros can serve as placeholders, but they can also be sandwiched in between other non-zero values that are considered significant. And so when we find that, just like we did on the balance a moment ago, we're going to consider these sandwich zeros to be significant as well. But there's a third rule that we want to look at as well that you can see. The zeros at the end of a number that contain a decimal are considered to be significant. And all 3 of these have 4 significant digits. Because this value has a 0 in it, then 2.410. All of these 4 are significant digits. Again, because I've included a decimal here, these 4 are considered significant. And this one as well. This 0 is a placeholder. It's not significant, but the remaining are because we have a decimal present in the measurement. So each of these have zeros that are considered significant because there's a decimal there in the measurement. Counted numbers or numbers that are defined are considered to have an infinite number of significant digits. Let me show you what I mean by a counted number. To see the number of peeps that are in this photograph, that's right, there are 10. And so if there are 10, then that value of 10 has an infinite number of significant digits. Why? Because we're not using a measuring device. This observation of 10 is not dependent upon a measuring device, but strictly our observation. So it has an infinite number of significant digits. Also, numbers that are by definition, for example, the number pi here, 3.1415 and so on. This is an irrational number. We actually need a very powerful computer to determine how far that number will go, and I still don't think that they've done that yet. But by definition, that's what pi is. And so that's going to have an infinite number of significant digits. Keep in mind all conversion factors as well. There are 100 centimeters that are in a meter by definition. And so that value, 100, is going to have an infinite number of significant digits by definition. Okay? And then we want to take one other idea, the fact that zeros are going to serve as placeholders. Those are the ones that are not significant. So as we go rapidly on to scientific notation, we want to take a look at some special rules that apply to scientific notation. First, that measurements that are expressed in scientific notation are going to follow the same rules that we just reviewed. That's great. There's no more rules that we have to worry about. But there is a concern that we have when we convert those values that are in scientific notation into an expanded notation. We're going to preserve the number of significant digits that value has. All right, so we're not going to change how significant that is. Let me show you an example of what I mean. So if we have the value 9.420, again that 0 is significant, times 10 to the negative third, we have 4 significant digits. Well, when we carry that over into an expanded notation like we have here, often our practice is we're going to underline those same digits which we consider to be significant. The other zeros that you see here are just place values to hold the decimal point where it's supposed to be. So again, both of these values have just 4 significant digits. Hope you're staying with me on that. And then we get into the area of calculations, and this may cause some confusion, but Keep in mind that different rules are going to apply to different kinds of math operations. But here's the basic concept. When we're taking one measured value and we're going to multiply it or divide it with another one, we have to take into account how many significant digits each of those have. And so as we look at multiplication and division, the number with the smallest number of significant digits is going to determine the significant digits of our answer. Okay, it's the value with the smallest number of significant digits. Now, that may confuse you. Why? Why are we going to limit ourselves? Well, I want you to imagine, for example, that you have this pair of earphones right here that was made in around 1920, okay? So it's very old technology. When you put those over your ears and you listen to something, it's going to sound very scratchy. The audio quality is not going to be good. That's also true if you were to take these wires that you see here and somehow rig them up to your smartphone. Now, the fidelity of the sound that a smartphone produces is very high. But if you take these earphones here that were made, 100 years ago or 90 years ago, and you plug them into a smartphone, they're still going to sound like they're 90 years old, okay? Even though the original signal is excellent. And that's kind of how when we're combining a very precise value to an imprecise value, the precision of the first value, it's not really going to matter anymore. Even if you were to reverse this, if you were to put high quality earphones onto a device that was made back in 1920, it's still going to sound like it was made in 1920. Make sense? And so we're going to apply that same kind of reasoning to our measurements. Now, as we get into addition of calculating and significant digits, here we have a value of 3 significant digits, another one with 3 significant digits, and here we have one that's only 2 significant digits. Now, if you were to put these all into a calculator, you're going to get this long decimal value. And that's going to be somewhat deceptive because really the precision of this measurement is limited by the 0.75 here. And so our answer is then going to have 2 significant digits. All right, now let's move on to those rules that apply to addition and subtraction. The concept is basically the same. We're going to limit the number of significant digits, in this case, to the value with the greatest uncertainty. Well, what does that look like? Imagine when you weigh yourself, right? Is the stuff in your pockets, or the things on your person, your clothing, is that going to make a difference on the scale? Well, you think it's probably going to make a little difference. Imagine if you were to take your wallet out and put it onto a balance and you get this value, or your comb, this value. Or if you take your ring and you put it on a really precise balance that we looked at a little while ago, we're estimating to the thousandth of a gram. But then your shoes, you don't have a balance that you can put those on, and you pull the box out and they tell you, well, it's 978 grams. All right, well, that's a lot less precise than what we're seeing these numbers at. Don't you agree? Fewer significant digits. And then clothes, 1,230. Okay, and it's not going anywhere past that. It's a whole number, 3 significant digits. But then you get on the scale, and the scale says 75 kilograms. We convert that to grams, so we're working with the same unit, and here we only have 2 significant digits. We go to add all these numbers up, and what do we have? Well, we have 75,000 grams. We have to really disregard the precision of these other values that you see on the screen because we have to limit ourselves to the measurement with the greatest uncertainty. Well, I hope that makes sense to you. We now have come to the end of our segment, and I know we've covered a lot of information, but I appreciate your watching. If you found my explanation of these rules helpful, hit the like at the end of the program, and thanks for watching. This is Tim Zietz from Linville Hill Christian School. Bye-bye.